Okay, picture this. You're sitting in the exam hall, the clock is ticking down, and you turn the page to a seemingly simple energy calculation. You punch the numbers into your calculator, scribble down the answer, and move on, completely unaware that you just threw away 4 easy marks. In this explainer, we're going to hack the Cambridge IGCSE Physics 0625 exam matrix. We're talking zero fluff here, just the exact strategies, mark scheme secrets, and structural frameworks you need to secure top band marks in energy and efficiency.
Consider this classic scenario. A motor transfers 500 joules of electrical energy into 100 joules of kinetic energy. The student calculates the efficiency by taking 500, dividing it by 100, and getting 5%. Seems like a reasonable attempt, right? Wrong. This calculation loses every single mark available. Not only is the math completely inverted, but it lacks the fundamental understanding of how energy transfers are actually structured. Now, if you've ever made a mistake like this during your revision, don't panic. You aren't bad at physics. You just haven't been taught the code yet.
And to really crack that code, we need to ground ourselves in exactly what Cambridge is testing. Section 4 of your syllabus, Forces and Energy, lays out the exact battleground. You'll see topics like work and energy transfers, calculating potential and kinetic energy, and efficiency and power. This section is an absolute goldmine for marks, but it is also where the highest concentration of student errors occurs. Look, the examiners know exactly where you're going to trip up, and they design questions specifically to test those weak points.
Now, what's really interesting here is what I like to call the matrix of lost marks. This is exactly why ordinary textbook revision completely fails you in the actual exam hall. You can memorize every single equation, but if you drop a joule or a watt, you lose the unit mark. If you round your numbers too early in a multi-step calculation, your final answer falls outside the acceptable examiner range. If your descriptions of energy stores are vague, or if you use the wrong variables entirely, out comes the red pen. And the most heartbreaking mistake, writing a beautiful conclusion that completely ignores the data you literally just calculated. We are going to fix all of this today.
Let's start with an immediate quick win to rebuild your foundation. Before we can calculate efficiency correctly, you have to lock this definition into your brain. The principle of conservation of energy. Energy cannot be created or destroyed. It can only be transferred between stores. Think of energy kind of like currency. You can't just spawn money out of nowhere, and it doesn't vanish into thin air. It just changes hands. Or, in our case, it changes stores.
In a moment, I'll show you the hidden examiner clue that completely flips how you calculate kinetic energy efficiency. But first, you need the framework to decode it.
So, the absolutely crucial point is this 4-step sequence. This right here is the top band answer code. Elite students don't just guess their way through exams. They mechanically construct perfect answers using this exact framework. Step 1, identify the concept. Step 2, pull the evidence or data straight from the prompt. Step 3, apply scientific reasoning to connect the data to the concept. And Step 4, lock it down with precise examiner wording. Let's take this framework and apply it to that painful mistake we saw at the very beginning of this explainer.
Let's move to Step 1 and 2 and see how this builds. Step 1 is the concept. What actually is efficiency? It's the ratio of useful energy output to the total energy input, not the other way around. Step 2 is gathering our evidence. Looking back at our motor, the total electrical energy going in is 500 joules. The useful kinetic energy coming out is 100 joules. We organize this data clearly before we even touch a calculator. Useful out divided by total in.
Which brings us to the correct calculation. 100 joules divided by 500 joules gives us 0.2, which is 20%. Just look at that number. It's clean, the math is correct, and it makes logical sense. A motor literally can't be over 100% efficient, and it certainly isn't calculated by dividing the input by the output. But we aren't done yet. A 20% efficiency means that 80% of that energy, 400 joules, went somewhere else. And if the examiner asks you to explain that, you're going to need steps 3 and 4.
Step 3 is the scientific reasoning. The missing energy didn't disappear, it was wasted as heat and sound. Step 4 is the exact exam-safe wording you absolutely must use. Do not write "the energy is lost." The examiner will penalize you for sure. Instead, you must write 400 joules is dissipated to the thermal store of the surroundings. The word dissipated is your golden ticket here. It proves to the examiner, without a shadow of a doubt, that you understand the principle of conservation.
Okay, you've mastered efficiency. Let's escalate the stakes a bit. You turn the page again, and you're hit with this multi-step beast. A 2-kilogram object falls 5 meters. Calculate its final velocity. Assume no air resistance. Well, there's no initial velocity given, there's no time given. How on earth do you find speed from just mass and height? This is exactly where standard kinematics equations fail you if you aren't paying attention, and where energy transfers completely save the day.
I want you to literally pause this explainer right now. Grab a piece of paper. Which equations link the gravitational potential energy store at the top of the fall to the kinetic energy store at the bottom? Write down your prediction. Force yourself to actively recall this, because this exact cognitive bridge is what the highest scoring candidates cross effortlessly.
Before I show you the perfect answer, let's look at where the bloodbath happens on the examiner's desk. Spot the physics error. Trap number 1, forgetting to square root the velocity squared at the very end of the calculation. Trap number 2, panicking about the mass. Fun fact, the mass actually cancels out on both sides of the equation, so whether it's 2 kilograms or 2,000 kilograms, the final velocity is exactly the same. And trap number 3, doing all that beautiful complex math and then forgetting to write meters per second at the end, losing the final unit mark. Brutal. Let's contrast a typical flawed answer with our top band answer code. On the left, the flawed answer. It falls, so it gets faster. Energy goes to movement, V equals 100. Vague terminology, no clear mathematical steps, and they forgot to square root. Now look at the right. This is art. First, the concept. GPE transfers to KE. Second, the equations. mgh equals 1/2 mv squared. Then, substitute the evidence. 100 joules equals 1/2 times 2 times v squared. Finally, the correct reasoning and wording. Solve for v, square root the 100, and you get v equals 10 meters per second. That is how you guarantee every single mark.
You now have the calculation code firmly in your grasp. You can track energy transfers, you can set GPE equal to KE, and you know how to use the exact terminology Cambridge examiners are desperately looking for. But here is the brutal reality. Calculations will only get you so far. What happens when the command word on the exam paper suddenly swaps from calculate to evaluate? Evaluation questions are the true gatekeepers of the highest grades. They require an entirely different psychological approach and a completely different set of exam-safe phrases.
If you try to answer an evaluate question using a calculate mindset, you will hit a glass ceiling. To break through that ceiling and secure those final, crucial marks, there is a deeper code you must learn. Are you ready to stop calculating and start truly evaluating your physics data? Your next mandatory step is to watch our next explainer, where we dissect the specific Physics 0625 command words that single-handedly decide your mark band. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. See you there!